Okay, folks, just for your information, we're going to start 5 after. Okay. Hey, Bill. Can you hear?
I'm here.
So, okay. Bill asked to say something so he could check whether or not his audio was working. So looks like it's working fine.
Just let me know when I should start.
Yeah, so folks, we are going to get started here. As this is a member-only session, I need to run the disclosures. And after that, Professor Guido will take over and run the presentation. Okay, before we proceed with any further, let me start with the disclosures.
Can't hear the audio.
Meeting times, obviously, there's a lot of competition for 7 a.m. Pacific time, and we try to accommodate as much as we can. So welcome to the meeting, and hopefully, if there are any questions, we can get them answered. You can always send mail to help@risc-v.org, and thank you very much.
It looks like we missed some parts of the disclosure, but I think the message could be seen. So to avoid running it again, so I think we are good to go from this point. So we have translated captions, so you can enable that if you want to, if you believe it's more comfortable to follow the discussion and understand better what's being said. And some common rules here. So if you want to, Professor Guido asked to let questions for the end of presentation, so he can go through the presentation and then we can ask questions. One thing that I would like to ask you is at the end of the presentation, if you want to verbally ask question, just raise your hand. I'm going to unmute you and let you speak. Or you can add a question in the Q&A tab here, so I can read that and then we can get that answer. So today's presentation is about using vectorization and matrix multiplication extensions to speed up convolution. It is going to be presented by Professor Guido, who is a full professor of computer science and engineering with University of Campinas here in Brazil. So Professor Guido, it's all yours.
Okay, so let me share the screen. Hope everybody see it. Is it fine?
It is fine. So if you want to go to present, yeah, that's way better now.
All right, so Thanks, Rafael, for the introduction. Just a very quick bio from my background. I graduated on compiler technology at Princeton last century, literally last century. So I've been doing compilers for a number of years. And this work is actually the partnership for the Universal Campinas and Celera design compiler design house. Okay. And so our agenda is going to be like this. We want to just quickly talk about touch base on convolution, because most of you folks probably understand convolution at this point. Then we are going to cover about this slice convolution technique that we have developed. And amazingly, it can perform better than Img2col BLAS. I mean, I know this is kind of bold phrase to say, but as a matter of fact, it does, because Img2col explodes the amount of memory that you need to use. So I'm going to try to convey to you that this is actually true, that you can do convolution without going through Img2col. In the third part of our talk, I'm going to discuss about our compiler flow. So our compiler flow for machine learning is entirely through the compiler, the MLIR and LLVM flow. And we show that we actually did that for the x86 and for the IBM POWER10 with mates with flight assist. And that's our baseline. We did that with the regular BLAS. And then we compare with the SConv algorithm running on the MLIR LLVM compiler flow. And at the end, I'm going to talk about in the future how we tend to port this to the RISC-V architecture. Okay. All right, just a quickly touch base in convolution. Actually, convolution, oh, sorry about that. Actually, convolution is a very simple operation. You have a kernel, and you have the projection of this kernel onto the input, and you basically do an elementalized multiplication accumulation of that results into an element of an output image, for example, in the case of an image. And you keep moving this kernel across the windows, take into consideration not only the current channel that you are, but the channels that follow after that. So you have the projection. We call here in our notation the projection of the window. So we have the first projection of kernel 0 into the input, the first channel of the window, and first channel of that you have of your image, and then you have a window, and you move the kernel to the side, and you get a new projection on the input. And this results in a new window, and then you generate all the windows for that specific kernel 0, and then you move to the next channel. And after finish all the channels for that specific kernel, you get another kernel, and then you continue for the next kernel. So this is a very basic operation that's well known. And but how do you do this? Okay. So the slice convolution algorithm has a flow in which we introduced three major components. The first one is an analysis pass. It's called convolutions nice analysis. And this pass has for goal to define a timing strategy and a scheduling strategy. And I will discuss about that in details later. The second pass that we introduced in the MLIR LLVM flow is it's actually two data transformation paths, an input and a filter packing. And I would like to call your attention to that, because packing is probably the most important task that you can do when you're doing convolution. People keep thinking, oh, maybe no, it's not. It's the timing strategy. Yeah, the timing strategy is important, but it's a reasonably well-known problem. Since Goto had its paper on how to do cache tiling for Jam. The problem is reasonably well known, so people did not have paid much attention to packing. And I would like to show you that if you do design a good algorithm with a very good and well thought packing, you can get very good speedups. Okay, so it's a very good source of speedups here. And these passes we're going to discuss about them. Okay, we're going to talk about the filter packing and the input packing later. And the third set of passes that we can use is called the convolution slicing optimization. The convolution slicing optimization takes the result of the styling strategy from the convolution slice analysis and do the actual work. It designed a loop nest, which is inspired by the go-to work on GEM. It synthesizes a way to do smart input packing, and it uses a microkernel that I want to discuss a little bit later. The tiling strategy is also used to do filter packing, and you do the filter packing at compile time, which saves considerable amount of time with your execution later. Okay, so you get the loop nest generated by the convolution slice optimization, the input packing, the microkernel, the packet filters, and you don't then do the lowering through the LLVM toolchain. Okay, all right. So let's go a little bit deeper into the convolution slice analysis. What is the role of this? It's a well-known problem, okay? And the focus that we did for it is to do tiling on the channel dimension. This is actually something that people have done before, and there is not much news here, okay? As for the tiling, the size of the tiles and the distribution, okay, in other words, the way you do the access of these tiles, the scheduling of the tiles, okay, we designed a very simple approach in which it's a very simple optimization heuristic in which we experiment with different number of tiles across the whole hierarchy. So we identify parameters K3 for L3 cache, K2 for L2 cache, and then we experiment what is the best combination of K3 and K2, which exploit or maximize the usage of the L2 and L3. And the third task of the convolution slice analysis is to define the order in which you are going to access. So you can keep, like, for example, the input stationary, the set input tiles stationary, and then you keep changing the await tiles, or you could do the other way around. This is also a known problem, but it's really amazing that depending on architecture, sometimes an input stationary is better than a wait stationary. Depending on the sizes of the cache that you have, sometimes, and for some convolution sizes, sometimes it's better, the algorithm outputs a better strategy based on input stationary or wait stationary. And we have realized that it's really interesting that for some architectures, you have more input stationary than wait stationary, like the case of Intel, and in the case of the POWER10 is the other way around. Okay, but this is actually depending on combination of the size of the convolution that the tensor size there, the architecture, and the size of the cache. And also for our scheduling order, we take the bursts in the DRAM in consideration. This is something that people have not looked carefully. I mean, you basically do the number as volume of data. Is not a smart way to figure out the best size of your tiles, because actually the DRAM burst, which has been extremely exploited in GPUs, had not been carefully looked at when you do the exploration of the tiling for neural processing units and CPUs with machine learning extensions. Okay, so you do consider the DRAM burst consideration. It's a metric that you use into our convolution slice analysis to output the tiling strategy. All right, let's give a very short example. The notation here is as follows. The green cubes here are tiles. The T here indicates tile, and the blue here is filter set tiling, and the reddish here is output tiles. Okay, so these are tiles, little cubes. And in our convolution slice analysis, we run this little optimization algorithm in which we want to determine the K2 and K3 parameters. And how it works? Basically, we use the largest set of input filter set tiles and output that can fit into the L1 cache. This the sizes of the tiles should explore the most of the L2 in terms of size, and should have a very good fit into the microkernel, which is going to be associated with your matrix multiplication extension that you have in your architecture. Okay, so try to maximize the size of this into the L1 and fit it with the microkernel. You can even recycle the microkernel that you have already designed into BLAS, for example. Okay, so the goal of the problem is to find P2 and P3. Let's consider, for example, the case of the future wake stationary. Okay, so we keep at L2 one input tile and a set of filter set tiles, and a set which is going to produce a set of output tiles. Okay, and what we keep doing is we keep it's the other way around. Sorry, we keep an input stationary here. That's the schedule we have. So we keep the input tile there, and we keep changing the filter set tile in between the L1 and L2 till you finish up computing the outputs, and the output gets cached back into L2. Okay. All right. So as for the P3, since we're talking about input stationary, we also determine the number of input tiles, filter set tiles, and output tiles that maximizes the size of L3. We don't use an LLVM programming technique for that. It's a very simple heuristic, and we try to adjust the tile size such that they maximize the use of L3 and L2, leaving L1 to be working with the microkernel that could come directly from BLAS. But again, remember, we're not using a library strategy here. We are basically using a full compile only approach. Okay. Let's move to the next slide. All right, so I don't go much into the details here, but for those of you who are ready, let's see if I can skip one slide. Yeah, it looks like I did. Yeah, okay. My little thing, my mouse, my little keyboard here is skipping slides. All right, for those of you who already know the go-to algorithm for GEM by heart, you're going to see that this is very similar to the go-to algorithm. It's similar, but it's not the same. What we basically did, we designed the go-to algorithm for convolution. We did an entire redesign of it, focusing not on GEM, but on go-to. Okay. And this is, I'm not going to go deep into the details of this, but each one of these layers here corresponds to 4 in a loop nest. Okay. And what the CSO strategy does is basically synthesize this loop nest. Right, and at the bottom here, what you're going to have this layer, last layer here, is the uses of your microkernel. And the interesting part of the SConv algorithm is that you can recycle your BLAS kernel. You realize that the BLAS kernel, which is auto product based, it has a very good fit into the way you design SConv. So if you already have a BLAS kernel microkernel working for your architecture, you can recycle it with SConv in Eclipse. Okay. All right. So as I mentioned before, you have all these layers which correspond to 4 loops. And inside our approach, this first set of layers 5, 4, 3, 2 correspond exactly to a find force calls. Okay, which are this, what is this affine? We are basically using inside our MLIR flow, we are using the affine dialect. So which one of these layers here, we have an equivalent affine for to construct a loop nest, and that's the role of the CSO convolution slice optimization. At the bottom here, in this last layer, we again have 154, which goes through a call to the microkernel. That's where the microkernel is called at this point. Currently, the microkernel is using one kernel dialect, but we are moving it to full standard MLIR dialect. So you have a set of 3 4 nexus force, okay, affine force, followed by the innermost one, which is a call to the microkernel. Okay, now that you talked about the microkernel, let's discuss it a little bit. It's an outer product microkernel. Okay, like the BLAS one. And you could encapsulate it and generalize it so that you don't need necessarily to go through a specific microkernel. It could be hidden behind some intrinsic for LLVM. It can be, as I said, as the same as the matrix multiplication. It could be the gem microkernel inside BLAS, for example, you could recycle it. And our goal is to encapsulate. We are not doing this right now. At this moment, our microkernel is a library and we're linking it to our compiler. But our next step, which is going to be, we believe, reasonably simple to do, is to encapsulate it inside the LLVM matrix multiply intrinsic. By doing that, you can have a toolchain or microkernel call, which is kind of independent on the underneath architecture. So in the future, if you extend your architecture, add more vector registers and do anything, you could redesign your microkernel there and couple it and hide it behind the LLVM mix multiply intrinsic, and you are done. Because the whole compile chain above the call to the intrinsic is going to be independent of their redesign bit for architecture. That's a very neat way to decouple your architecture design with your compiler flow. Okay. There is another alternative to that we are going to start a discussion with the MLIR community about not using the intrinsic of LLVM because this is an LLVM intrinsic, but using an MLIR-centric approach. But this is going to be defined in the future. For the moment, we're going to stick to hiding the architectural details behind the LLVM intrinsic. Okay, so let's go back a little bit and talk about the SConv algorithm. Okay, so just to recap a bit, you have a kernel. You move this kernel on top of you project it on top of one channel of the input, and you get a window from the input. You move your kernel to the side, for example, and you're going to have another project on the input, and you have a new window. Okay, so keep these two concepts of windows, which are projections of the kernel on top of the channel. Okay, that you're going to need it. All right, so we did this for the Intel x86, and we did this for the IBM POWER10 with a matrix multiply assist. Okay, this is a previous work we did as a research together with IBM. Okay, and the code is running perfectly on POWER10 and it's working smoothly. Okay. All right. So, so how did we did for the MMA? Okay. You're going to see a little bit of some issues raised here a little bit. How would this go through into RISC-V, like the 20 MED, for example, or for some future matrix multiplication extension? Okay. For RISC-V, but I don't know. I will touch base on that later in this talk. Okay. Okay. So what you have is a kernel set, and you have the windows, the projection of the kernels. So what our algorithm is outer product based. Okay. What does that mean? Mean that we basically store as each element of a vector AVSR the first element of a kernel. For example, A here goes into this A here. And the next one element of this vector is going to come from K1. So J here is going to go here and so on. So this VSR is going to store the first element of each kernel. Okay. All right. So you're going to do the auto product with the window. And the window also, we're going to have the same pattern. You're going to take the first element of the first window and the first element of the second window and so on. So we're going to see how we're going to do that. How do I fit the NCHW format to this? That's where the pack kicks in. That's the very one of the most important transformation. You could do that like replicating data and building these huge matrices using Img2col, or you could do that using a smart packing approach. Okay, so our approach to packing that I'm going to detail further later does that. Okay, it takes this first element of each one of the kernels, the first element of each one of the windows, and assign them to vectors, to the VS0 here and VSR2 here. Oh, this is, by the way, the notation that is used inside the IBM vector registers. Okay, so in general, what you are doing in a logical sense is this. I'm linearizing my window across the vector registers. And then I'm loading those, but I'm not loading this directly from the layout that you have for the input. I'm actually doing a packing step before that, because by doing the pack step, I increase the locality in cache, and this considerably increases the performance of the output. Okay. All right. So for the second window, I do the same and do the packing, and the packing generates this layout with the vector registers. We keep like in a linear manner, touch the cache, which considered, as I said, improves the locality and reducing cache misses. I do the same for the kernel, and then kernel 0, and then the kernel 1, and so on. Okay. All right, so this is just logical, right? What happens actually is a packing step before you do this. You load the vector registers. Okay, now that the vector register 0 is loaded and vector register 2 is loaded, I do the outer product. And there are many design points for that in terms of hardware. You could have like an inner product based systolic array approach. Okay. It complex 3n minus 2, where n is this, one of the dimensions of the matrix, the input matrix. Or you could do like IBM did, and not sure, maybe Is1T MEB did as well. Use like a grid, right? You put your vector registers on the side of the rows. You put your windows element, your other vector register on the side of on the columns, and you do just matrix multiplication or a product all at once, right? You do 16 maps at once. So each entry here gonna have a map. So there's no this notion of systolic array for the outer product permutation. All right, so in the IBM, what's gonna happen? You're gonna accumulate that. Okay, for example, just two multiplication because it's an outer product, K0W0, K0W1. Into two different cells, but it's just illustration. But because what you do is basically you do another one just for K1, but all this happens in parallel. And by doing the whole VSR outer product with the VSR2, that's the notation of the outer product, you get a full matrix result at the end, okay, after a number of cycles. So there is a trade-off in the hardware design for this, right? Should I do a systolic array, which has some complexity, or and probably going to have a faster clock cycles, or should I do a matrix multiplication where the gates are going to have a larger fan out, and you probably might have a little bit larger area, and maybe, but it's going to be faster somehow. Okay, so that's a hard design choice that I didn't want to discuss here. But anyway, you get this full 16 matrix as a result from a compiler point of view, logical point of view. But in the IBM case, they have like 8 accumulator registers. Okay, so you can play them around and do your algorithm using all the 8 registers. I believe the Is1T has also 8 register matrix register as well, right? Okay, so let's go into the packing, right? That's one of the tasks of CSO. For the packing, we do exactly like this. We do a pre-packing of the input. Take the first element of this is the red window here on the input. We take the first element of it and move it here. And then move the window to the side. So the reddish window goes to yellow window. And then take the first element of this one, move it here. First element of the black window, move it here, and then start with the second element. Second element of the first window, second element of the second window, and so on. Okay. All right. That's an input packing. And we notice in our experiments that's such an important task for CSO that we devoted a lot of attention to it. Okay. So one observation you notice while you're looking at this is that for stride 1, the second window vector is just a left shift of the first one. That's not new. A number of researchers have found this. People have used this, and you said, okay, so if you take the V0 register and left shift it for the stride 1, we could get the V1 for the next iteration. Okay, and since stride 1 is fairly common, okay, we noticed maybe we should go deeper into doing this in a faster way. Okay, so what we did, we basically tried to find a way to concatenate vector registers, okay, to do our packing. Okay, so the idea here is if you could in your architecture have 2 vector registers, enable a sort of vector grouping in V extension notation of this register and logically move them together, we don't need to do this in memory. Okay, so the idea is exactly that. We take, for example, V0 and V1. If we logically could concatenate them and shift them to the left, so the 2 here goes into 1 and result in this, the 3 here goes into 2, result in this, and we take the 6 here, move into the 5, and the 5 move into the 4, we could, by just using this vector group shifts to the left, get to the next iteration that we need for our SConv algorithm. Okay, so we said, okay, this is probably very important because we don't need to do this in memory, which is going to be costly. So the next step was, could you do this in the current architectures? So that's exactly where we looked for. And we found that for AVX 512 and the VSX extension of IBM, they allow that. Okay, so we could take 2 vector registers and kind of concatenate them, left shift them in group, just remove a few entries here in the vectors that you don't need, and get what you want for the next iteration without going into memory. Okay. Of course, if you could do this in a large set of vectors, all right, in parallel, this could be very fast. And you don't touch memory here because touching memory is a sin. You shouldn't touch memory, okay? It's very expensive, right? So, but how we do that in the compiler? We actually use the vector extension. Okay, there's a vector extension in MLIR, and we could design the vector shuffle instruction in MLIR to do that. And that's exactly what we did for the packing. It's a technique that we call VBP for vector-based packing. All right, so let's go for the experimental setup. Okay. So what we did is we ran this on the IBM POWER10 E1050 CPU at 4 gigahertz. It was actually, we're very lucky because in the middle of this project, we got the IBM POWER10 release, a real machine to work on, right? Because sometimes you do this in simulation, it doesn't represent, even if it's cycle accurate simulation, it doesn't represent actually what's happening in the machine. So with this project with the IBM Toronto group, we managed to do this in a real machine that we can reserve execution on metal-based execution, not through virtual machine execution, and actually could do real measurements of the machine. So this machine has a single thread, single procedure computation speed at 256 gigaflops, and has an MMA matrix engine, which allows 2 order products operation. Okay, so we could do two MMA operations for the gems, and 1 accumulation per cycle. Okay. We also did these experiments on Intel Xeon Silver CPU with 2 gigahertz, 2.1 gigahertz. Again, a single thread, single precision computation with a peak of 67.2 gigaflops. using the AVX512 CMD, which allows one FMA operation per cycle and 2 operations on 16 F32. For the experiments, we did 100 measurements with low variability, directly on the hardware, not virtual machine. And for the environment, we used the Onyx MLIR environment. We did use the Onyx MLIR because it's kind of interchangeable in between all protobuffer and all the formats you have there, and that because they have an MLIR kind of lowering from the Onyx model, okay? But I mean, not necessarily needs to start with Onyx. It comes from PyTorch and go down to Linalg or some other dialect, okay? And we did this for full machine learning model. We didn't just do the experiments for convolution, okay? We did for full machine learning models. And we measure against Img2col, that's our baseline, Img2col plus Open BLAS for these architectures. So please notice that the Open BLAS for our baseline is the Open BLAS with MMA, okay? So we compare with Img2col plus Open BLAS with MMA, and we managed to show that doing a kind of improved packing and doing the tiling from SCSA, you can get better results than using the Open BLAS with MMA. Okay. Of course, our compiler flow will also use MMA, but it's on a compiler only flow. But the point is that we skip Img2col. Don't build that huge matrix with lots of guest misses. All right, so let's go into the results. All right, so we experiment this with these 7 models, okay, CNN models. We measure the convolution speed up for x86 with AVX and POWER10 with MMA, and we got these speed ups. Okay, just I'm gonna make it really clear. These are speed ups on top of Open BLAS with AVX512 and Open BLAS Img2col, right? Img2col plus Open BLAS with AVX512 and with MMA. Okay, it's a reasonably good speed ups, but only for the convolutions. Okay, I'm comparing here convolutions of all the convolutions on these models, all convolutions for the baseline and for our SConv algorithm inside the MLIR compiler. All right. But when you look at the model speed up, the whole model speed ups, it's not very good numbers, right? I mean, we managed to speed up for example, the convolution for the VGG16 model 28%, okay? But at the end of the day, this only reflect on the POWER10 12%. But the reason is, of course, is the share of the convolution in the model, right? For the POWER10, the share of the convolution is only 40% of the whole execution time for that model. Okay, so you get improvements for convolution, of course, but the rest of your implementation for your model, the ReLUs and all the operators should be good, well implemented, right? Otherwise, we're not gonna have the impact of improving convolution. Okay. Look, for example, for the ResNet here. You have 46% of the POWER10 improvement on performance, right? But given that the convolutions of the ResNet 18 is 82% of the execution time for the P10 model, this reflects on 42% speed up on the whole model for that network, okay? So the message here is improving convolution is important because it's important operation inside a model, but you have actually to be really focused your energy on the other operators, okay? Because some of the other operators sometimes require reductions, which are very expensive operations, and you should take care of them as well. All right, so just a slide reflecting the whole model speed up. Okay. All right, but how are these are book numbers, right? What I just showed you, but how they are reflecting on the individual convolutions? So we did that for the POWER10 and for the x86. So we ordered the convolutions. We had 393 convolutions in all 7 models. We ordered them according to the speedup and the x-axis here. And for the y-axis, we just plot the speedup. So and the baseline here again is the Img2col BLAS with MMA on POWER10. So this crossing here indicates the point where it's not worth it to use SConv anymore, right? I mean, you have but for 90% of the convolutions, we managed to give speedups. Okay, that came from like almost twice to, well, actually kind of tying with the Img2col BLAS. Of course, it would have some hybrid approach in which you just check the profile of these convolutions here and see what you can do about them, okay? And or maybe switch to Img2col BLAS for them, but it's probably not worth it, okay? A similar number also showed for the x86. In x86, we managed to speed up 91% of all convolutions on all those models, okay? And for this tail here, which corresponds to convolutions that Img2col BLAS produce a better result, we went deeper into it. We have papers on this. I can send you papers if you want on all this. But the point is, most of these convolutions here are pointwise convolutions. So what is interesting is that our approach managed to speed up even pointwise convolution, which is basically a gem, okay? And most of these convolutions on the tail here are pointwise convolutions, okay? But a number of pointwise convolutions are also on the left side of this point here. All right, so why does this thing work, right? You basically don't do Img2col. You do the timing. You are using a direct convolution approach, right? And so why at the end of the day it works? It works because of reduced misses in caches. Okay, so we have the suspicion that the technique improved locality, cache locality a lot. And so we did this experiment. We measured for all models. We measured the base. The base here represents Img2col plus Open BLAS. And SConv here is our technique, direct convolution compiler-only approach to MLIR plus LLVM. And we measured the cache misses on L1 cache and L2 cache. Okay, as you can see, for most cases, we kind of halved, a little bit larger than half the number of misses in the L1 cache. And that's where the performance comes. This reduction on the misses come from 2 major sources. The tiling that we are doing, the fact that we are considering bursts, memory bursts into our exploration of the tiling space. And it also comes from the vector-based packing that we're doing, because we're not touching memory. We're doing things in vector registers, okay? So it's a considerable reduction into L1 cache, this rate. And also for L2, right? And the numbers here, although the cache misses in L3 for L2 is smaller, of course it's smaller, right? Because I mean, caches are for that. You don't want to touch caches frequently, right? So the cache miss rate on L2 is smaller than the cache miss rate for L1. But we managed even to do a very good reduction into on the number of L2 cache misses, which is larger than kind of reduce it to a quarter maybe, okay? Sometimes even smaller than that. And okay, so why does it work? Because it considerably improves locality. With all these huge workloads that we have on machine learning, reducing cache misses or reducing data movement as much as we can is the most important thing. the max, the multiplying accumulates we're doing, I mean, cost nothing because you can do them in parallel. It's very regular, and you can have as a large engine as your SoC budget allows in silicon real estate. But moving data around is a really important metric. All right, so we noticed that, okay, we reduced considerably the amount of L1 misses and L2 misses, but what was the improvement specifically for the packing? Now that we are doing packing with vector registers, you're not touching memory, okay? So what we did this breakdown on the execution time for the POWER10 and for the x86 for packing, which is represented in pink here, for the execution of the microkernel, and for the rest of the computation, okay? So this pink bar here, sub-bar, means the amount of time for the whole execution of the convolution was devoted to packing. And we measure that, and we measure how much time you're spending in your microkernel, the blue sub-bar. That's the most important thing. You want to expand the most time of your execution time on the microkernel, right? Because that's where the computation is done, right? So as you can notice, for the base, you have like a 40%, a little bit less on packing, and because you're doing Img2col, right? In the base, we are considering packing Img2col as well, and you are doing 60% or a little bit more on microkernel. So it's not a very good distribution on preparing data, like packing Img2col, and doing the real work, which is the microkernel. You want to increase the real work, right? And so half and half of those is kind of not that good, right? I mean, you don't want to spend time preparing this overhead data for your execution, right? So we can see, for example, for the Google Net, most of the time, because we're doing this fast packing, most of the time the computation is devoted to the microkernel, which is good. That's what you want, right? So for all the cases, you see that the blue sub-bar increases because you are doing packing really fast, and thus a larger share of the computation is on the real work or the microkernel. Okay. All right, so we did this speed up for the packing. Okay, so we took the whole speed up and we broke it down and looked at what is the speed up for the packing only. So if you do consider the base with Img2col, but the packing, which also happens inside BLAS for the traditional approach on the x86, and consider that as the baseline and measure the time we spend on packing on the SConv algorithm. Because of that, we are using the VPP optimized approach, we managed to get packing speedups. So be careful there. It's speed up just for the packing of the order of 3 to 4. Okay. We did the same measurement for the POWER10, and the packing speedups is also of the order of 3.5 to around 7 speedups on our packing. Okay. Again, disclaimer: this is speedup specific of the packing. All right, so we'll move a little kind of faster here. Up to this point, I showed an approach, compiler-owned approach based on MLIR and LLVM toolchain, which uses a microkernel from BLAS, just for the inner core, which is machine-specific, architecture-specific. But I didn't talk much about RISC-V and this name Celera that I mentioned in the beginning, right? So let me just go over these two names, and then I will connect with the next steps for porting this approach to RISC-V. All right, I'll talk very quickly about what is Celera. You can think of Celera as a spin-off of this project. Okay, it's a company which has been doing compiler development work for the last 2.5 to 3 years. It did compiler servers for LG, for AI-MIM future, which has a neuromorphic engine, and for a research institute in Korea called ETRI. And I'm going to talk specifically for the compiler toolchain. We worked with the AMI feature. AMI feature has this NMP neuromorphic engine. What is this engine? This engine is a very neat design, actually. It's a 32 RISC-V based cores. Okay, it has 32 RISC-V cores. These cores are divided into clusters, and these clusters organized into larger clusters. Okay, how does it work? You have tiles, say for example 4 tiles, and each tile has 8 tilets. So let's look at tile 0 here. You're going to have tilet 0, 1, then tile 7. And each tilet is going to have one RISC-V core extended with machine learning accelerated instructions. Okay, so you extend the RISC-V and you throw like a 3D convolution instruction there, you throw like a ReLU instruction there, etc., which all are based into a MAC unit. And these MAC units read 3 scratch pads. It's not a cache-based design. It's a buffer-based design. So the compiler has all control on the data movement, which is really good. I mean, you don't trust on the kind of uncertainties of cache hierarchy. So one scratch pad is used for the input, the other one for the weighted output, and it can be as large as you want, and you can do a number of MAC units in parallel. Okay. It also has some fast DMA engines, right, and a read network to connect all these tiles in between among each other. Okay. So that's the design. On chip, you also have an ARM host to do the basically preparation, building the model and running the compiler that we have designed, and then spread this across the tilets and using the schedule that the compiler defines. So we did this compiler design in partnership with MI feature on the neuromorphic engine. It's a separate design, not related to this other project we did as research, and which is moving also into an extension for this RISC-V in the future that I just mentioned before. All right, so Celera tool chains that we have experimented with. Sorry about these big arrows here. That's what happens when we don't test carefully from PowerPoint, the local machine, and then go into Google Slides. But we do, we experiment with this using the SCSO inside XLA compiler, using a Keras TensorFlow and NMP LLVM based front end that runs on RISC-V, those 32 multi-core RISC-V architecture, the NMP. We also did that with the Go flow from Meta. We take Onyx, move it to Glow. We also take PyTorch, move it to Glow, and then go into the Glow optimizer and quantizer. And then we have the ESSO technique here. And then move it to an NMP, and then RISC-V toolchain as usual. Okay. We also experiment with the RISC-V simulator as well, okay, as part of this tool development of these two chains. So as you can see, the CSA and CSO technique have been used here for neural processing units. So it's not a technique that you can use only for CPU-based hierarchy, memory hierarchy, okay, kind of architecture. You can do that for an architecture where you have you don't have caches, you have scratchpad buffers, and you have full control on the access to the data. Okay, so enough from Celera. Let's go back a little bit about some issues that could show up on port SConv for RISC-V. Okay, so this is kind of exploratory part of the presentation. Okay, and I really would like, we are very open to receive feedback, questions, and participate in the process of the MATBU extension, so we can explore and give some contributions about this. The first question that showed up with me on this is, what is the state of the current MATMO extension? I know about the ZMT, MEV. I know that the standards is going to be moving into some definition. But some questions would be really important to understand kind of very early on. Like, is it going to be an inner product or systolic based design, a hardware design, or another product, MMA, or even ME? I'm not sure if ME is a systolic or a product based. Does this make a difference? A little bit, right? Because our algorithm is our product based. We could retarget it to be an inner product based design. We have to give some thought and how to rethink the algorithm for that. Okay? It might be just a matter of doing a different packing, but you have to do look at it carefully. The other point that raised to us is that going to recycle the VRAG space from V extension or not? Are the matrix kind of storage going to be mapped virtually or logically on the top of the vector registers? For the MME, as far as understood, it's not. It's a separate extension, has its own set of matrix registers. Okay, but this might have some implications. Remember, sometimes you want to do the shifts on set of vectors inside the matrix. For example, this might be a little bit different if you don't have this logical map of the matrix on top of the vector registers. I know that, for example, the S1T has these NSR instructions that you could do that, but it's not clear if you can concatenate registers there. Okay. The next question is, what is the state of RISC-V MLIR lowering? We trust the affine dialect and the vector dialect to do parts of the lowering, okay, to LLVM, towards LLVM, but it's not clear to me if these things are kind of being explored in a RISC-V LLVM MLIR toolchain. The other point is how to design intrinsics, okay, for RISC-V for the our product, right? This is more like a firmware hardware designer point of view. So you do have all your low-level intrinsics for your or your assembly instructions for your machine, and encapsulate them in little C-level intrinsics. And how do you put that together in a nice LLVM matrix MATMO intrinsic? If you can hide that properly, I mean, everything that talked above, you don't need to worry anymore. It's because the compiler is going to take care of you, and you nicely encapsulate and hide all your hardware behind the intrinsics. The only thing which is going to be on the toolchain I just talked to you before, specific of the architecture, is we need architectural info to feed the convolution light analysis to know the size of the caches, so we can do a proper tiling. That's the only architecture specific part of the SConv algorithm. Other questions are how to handle the vector-based packing RISC-V. Okay. I know that I have looked not in details. I'm not an expert on the RISC-V extension. That's a disclaimer here. I read this S1T spec, preliminary spec, and I'm still reading the extensive the extension for RISC-V. But by looking carefully in some part of it, I noticed that there is this vector-based shift left registers that could be kind of vector grouping based, which would be equivalent to what it did for the POWER10. And the NSRA shifts that you do at rows at the matrix could come in handy for that, provide that to be somehow concatenate, enable the concatenation of register, which is not clear for me at least at this moment. So the other question is, what is the SConv potential for ZT and Sci5 X280? And are there other MATMO extension proposals out there? I just saw the preliminary for this ZT MEV, and if there are others, please let me know. And this etc. here is a bunch of questions, okay, that I have, and and would like to discuss. I'm pretty much open to discuss that. All right, so we're coming to a closure to the talk. Okay, so what is the role of Celera on this? Celera is looking for a sponsor to port the SConv for the RISC-V technology. Okay? There are a number of questions that need to be answered, at least from the point of being able to port SConv. As part of this project, we could do some architectural exploration, have like a spike or some simulator here, while the real hardware design for matrix multiplication is not done. We could explore that. The SConv approach already showed that can be better than Img2col BLAS. We could, of course, as part of this project, explore this the BLAS flow as well, because it's really nice. I mean, the Img2col BLAS is not that bad. I mean, you can design a microkernel fast, embed it into the BLAS, and do Img2col, okay, and get a baseline for your design really fast, right? But the nice thing about SConv is that that same microkernel that are embedded into the BLAS, you can put it behind the intrinsic and use it on the compiler flow with SConv, right? So there is some exploration there. There's a lot of work to do, and actually Celera is looking for a sponsor to do sport. Okay. If you are interested in things I mentioned, I mean, we have two papers that we can mention, give to you, like the paper which describes the application of the CSO and CSA technique on the neural processing unit from NNV from AMI Future. Or we have also papers, the IBM folks, when you did this whole design for the POWER10 and x86. We're going to be at the TinyML 2023, which is going to happen soon, a week from now, approximately, from the 27th to the 29th of March in the Bay Area, close to San Francisco. And Celera is going to be there in the poster sessions. So if you happen to be in the Bay Area and you want to discuss that in details, we have a whole set of descriptions, and we can discuss that, how this could be a potential algorithm for RISC-V. All right, so I'm gonna end the talk here. So thanks for your time, and good morning, good afternoon, good night, right? Okay,
thank you, Git. We have some questions here. So
sure.
we have 4 questions, I believe. The first one that comes from Adrian. He asks why LLVM MLIR instead of Apache TVM.
Well, you could do TVM, of course. What happens with TVM? And by the way, I know pretty much Luis there is a very nice person, and we chat about this once. TVM is a very exhaustive machine learning based way to find the loops, to find the best tiling. Okay, let's find the best tiling. Let's define the best set of loops. The point is, how do you evaluate that with a little bit different architecture? Like, for example, that architecture I just mentioned, which is very complex architecture, where you have 32 cores, it's a multi-core architecture, you have multicast instructions, modeling the kind of different complex architecture engines for machine learning, okay, on TVM is a little bit more complex than doing that for a regular CPU or GPU, like TVM does. That's one thing that we could do. I mean, we actually want to, we are already doing that actually. We take TVM and try to use the machine-based approach to learn the best loop nest. But in our experience, when you start throwing complex architecture complex on it, it has a hard time to find the best design point.
Another question here from Michael is, what data formats do you support? And I mean, and adding to this question is, do you mix data formats? Is there any specific data format that you need to handle?
Okay, at this moment, we are not just dealing with the basic floating point integer data types, okay? And, it's not that hard to have that because LLVM has all the data types embedded into the instructions of the dialects. So doing that would not be much complex to go beyond that.
Another question from Michael is, what is on your wish list from hardware implementations? What would you like to change?
Oh, that's a good question. Yeah, it's I have a background in microelectronics, right? And in my progressive life, I mean, when I did my master's in microelectronics, so I love hardware a lot. So it's not clear to me. I'm not a hardware designer, right? I end up in compilers, but I really would like to get a little bit insights about outer product of our solid base inner product. What is the best design? It seems to me that with this very small transistor feature length that you have today, you can afford to have an outer product which is efficient. I believe that MMA design is a very good, well thought hardware design, and it's really fast. So I would stick to the outer product, hard matrix multiplication unit. Okay, but it's just kind of a little bit of guess from my side based on the experience that I have on hardware design. I just did a few hardware design before the PhD. But I'm not an expert on hardware, okay? I wouldn't say this one is best, but I would stick with another product design.
Another question here from Peter. Can you apply the techniques you described here on a set of small matrices?
If the hardware has a set of small matrices, right? That's the question, right? So I understand.
No, let me read the full question here. So the discussion seemed to be mostly focused on powerful vector engines processing large convolution operations. Would the techniques here also apply to smaller vector engines operating on small matrices?
Oh yeah, absolutely, yeah. Because most of the optimizations focus on the cache hierarchy. Okay, if you have a cache hierarchy, SConv is going to help you to do fast packing. It's going to help you to do like a good tiling. Okay, so if you have like an embedded design, have a rocket ship with this little Gemini, for example, let's consider Gemini engine on the side, and what SConv is going to give to you is the ability to have the data in the cache already when you need it, even if your engine is small. Okay, it can help you. And then it comes on your question, thanks for the question, because it just gave me an idea. Since packing is so important, it might be interesting to experiment with an extraction extension, which basically does packing really fast. But of course, you can use the VX extension there with vector groups, okay? Yes, the answer is yes, okay? It's independent on the size of the vectors that you have.
Okay, I think we do not have any more questions in the chat. I think one of the suggestions, Guido, is we can ask the questions you asked here and put that in the upcoming, let's say, vector or matrix seek or special interest group or task group that's being formed. So when we get that, maybe that's a good place to be part of and ask those hard questions you listed about RISC-V plans.
Yeah, sure, definitely. I'll be happy to contribute. Absolutely.
So, folks, any more questions before we close this session? Let me give it 5 to 6 seconds here. Oh, one more question just emerged. So, how does the microkernel map to RISC-V registers? And it is vector length agnostic. Will then matmul extension be matrix size agnostic?
Okay, the intrinsic, basically, as far as I recollect, it gets pointers. Okay, so you provide pointers to it, and you have to deal with the size inside the microkernel. Okay, so if your architecture has like 512 registers or have just 64-bit registers, you have to deal it inside the intrinsics. Okay, so it's a hardware like issue that you have to do with that. Okay. Sorry, could you repeat the second part, Rafael?
Yes. So and it is will matmul extension be matrix size agnostic?
Yeah, that's a good point. Yeah. I do not know how to answer this question, right? Because the standard is not defined yet. But as far as I understand, for the MME, it's not clear. I might, they have some size of matrices there, right? I mean, because the hardware is fixed, right? You can't, if you have this like say 4x4 32-bit hardware, you can you should block your tiling such that it fits into there for your microkernel. Okay, it might be that we could have like some sort of virtual register with arbitrary sizes. I believe that the VX extension does this approach, right? And this would be very neat. But I could relate the answer to this one to another previous question, which is, should we map the matrix on top, logically, on top the vector registers? This is something the standard will need to define. And what I could contribute to that is, for the packing, we definitely need to concatenate registers and move them concatenated. What worries me of not having the matrix on top of the virtual registers, and IBM does that POWER10, right? Is that you might need to move data from the vector register to the matrix all the time if you want to do some operations that the matrix doesn't support. Okay, so I have a little inclination to go to a design which the matrices are mapped on logically on top of the vector register set.
Great. I think now we do not any more questions, folks, before close now. And so okay, I think that's it. So thank you very much for your time. Thank you for the presentation. Folks, the recording will be available in 24 hours. Once available, I'm going to send you all an email with the links for the recording and the link for the presentation, so you can check it out later if need to be. So again, thank you very much, and stay tuned for the next session. Thank you very much.
Thanks, folks. Take care of yourselves. Bye-bye.